Okay, so before we jump into the slides, let me just try to give you the idea and the motivation behind this last topic, which I said was eigenvalues and eigenvectors. Right? Eigenvalues and eigenvectors, and we'll just look at a rough example of it, and you'll see the idea of it, and then we'll go into the slides and we'll go through all the rigorous definition of it. So the example, this would be an example in the vector space R squared. And the reason for that is because I could easily draw this vector, these vectors in R squared, because I'm going to say, let's agree, or let's write the vectors in R squared. For this purpose, we know that the vectors in R squared as a column, x comma y, instead of its usual. Okay, so usually vectors in R squared, we would write it in this way. But I'm saying for the purpose of illustrating and doing this example for eigenvalues and eigenvectors, let's write it like this. Okay, and the reason for that is because this will allow us to denote a vector by an arrow. Okay, so we're going back to the definition, or maybe the idea of a vector that you would have come across in your high school class, which was that vectors were, some sense, arrows. Okay, so so this is your R squared, right? So that's a vector space. And what I'm saying is, let's say I have this point here, and this is x, y. So this is an element, x comma y is an element of the vector space R squared. I'm saying I'm just going to illustrate it or, or denote it or maybe visualize it by an arrow from here to here. Okay, so this would be the vector x, y. So that means for each point, now you can think of it, for each point in the plane, it has a vector associated to it, right? So there's a vector 1, 1, 1, 2, pi 1/2, and so on. So for each vector in the plane, for each point in the plane, there's like a vector, like an arrow joining that to the origin. Now we're going to define on R squared a linear transformation. Okay, so now we're going to define this linear transformation from R squared into R squared. Okay, so it's going to take one of these XY points, one of these arrow, and it's going to give you another one. And how is it going to do it? So it's going to take T of, let's say, XY, and it's going to give you an answer. And how is it going to do that? It's going to multiply. Okay, so maybe I want to avoid using the letter X. Okay, let's use V. Okay, so let's call this guy the vector V. So T of V, and it's going to give you a vector by working out what is A times V. And what is big A? Well, that's a matrix. Okay, so where the vector V is given by x comma or xy. And A is a 2 by 2 matrix, A, B, C, D, right? So let's matrix multiply this. Well, okay, we don't need to get the full matrix multiplication, but we know that if we take a 2 by 2 matrix and we multiply it by a 2-row, 1-column vector, the answer will also be 2 rows, 1 column. Okay, so let's denote the answer by, let's say, x prime, y prime. Okay, so in other words, what we are doing when we take an element of r squared, and we multiply it to the left by a 2 by 2 matrix, is we are sort of, you can think of it like we are permuting elements of r squared. You give me an element, x comma y, and I will multiply it on the left by this matrix, and I will give you another element, x comma y. So the output from this, maybe it puts that guy, I don't know, maybe it puts it over here. Who knows? Okay, it will obviously depend on what the matrix A is. Okay, so it puts, okay, it's a bad line. Let's see. Yeah, it's better. Right, so that's the output. So it took that red vector, that red arrow, and it moved it to the green one. And it's going to do that for all the arrows. Okay, for all the arrows in the plane, each one of that, this sort of linear transformation by matrix multiplication is going to move all those vectors to other vectors. There will be, of course, one vector, the 0 vector at the origin, given by 0, 0, right? So there will be the 0 vector over here that it's going to remap to the 0 vector. So the 0 vector is not going to, it's not going to move. Go back to the top. Yeah, eigenvalues, eigenvectors. Was it this one that you meant? Or you meant, okay, or you meant start the explanation over back from the top. Right? This is sort of like, um, we haven't rigorously defined anything. This is just the motivation behind um, this eigenvalues and eigenvectors in R squared. Okay, of course, we're going to define it for any general vector space and any general type of linear transformation. But usually, this is the way I think about it. Okay, so good so far. So what we have is we're in R squared, where we say vectors look like arrows from the origin to that point. We define on R squared this sort of linear transformation that eats a vector in R squared and gives me another vector in R squared. And how does it do that? It takes the vector in R squared, this is the vector V, and it multiplies it to the left by a matrix. And of course, this is a 2 by 2 and this is a 2 by 1. So the answer is a 2 by 1 matrix. So it outputs another vector in R squared, and I could, draw that vector over here, right? I don't know why this one's staying. Okay, never mind. And I said that the 0 vector is going to be remapped to the 0 vector. So now the question is, are there other vectors? I can get rid of that one. Now, the question is, are there vectors? Here's my question. Question. Are there vectors such that when you do the matrix multiplication, A by V, right? The answer is the same vector that you put in, but it's a scalar multiple of it. So this is a scalar multiple, right? So are there vectors such that when I do the matrix multiplication, the output vector will be something like this. So the output vector will lie along the same line as the input vector. Okay, it should be along the same path. Let's, okay, right, okay. Let's take it to, and just stick with this one. So are there vectors that lie on the same line? So this would be lambda times the vector v. So are there vectors such that when you do this matrix multiplication, they get remapped along the same vector, but they are just either bigger or smaller, or maybe they point the opposite direction. That could happen. That's if lambda is negative, right? So we're looking for vectors that the matrix multiplication doesn't move that vector, but it just scales that vector. Okay. Now, notice that the zero vector is one such vector. Okay, because if you do A by the zero vector, that is of course equal to 0. And that is of course equal to lambda by 0 for any value lambda. Lambda is just a number, by the way, right? It's just a number. So the zero vector will always, the zero vector will always, right? Let's call this equation 1. Will always work in equation 1. Okay. What we are after is, are there any non-zero vectors that will satisfy equation 1? Okay, so we are after the non-zero vectors. The non-zero vectors that obey equation 1. Okay, so so the main equation in this section is going to be this: a matrix times a vector. So now when I say vector, I'm thinking a column of numbers. Okay, a column of numbers. So maybe I should draw it like this. So this is a matrix. This is a so the matrix will always be square, by the way. Okay, eigenvalues and eigenvalues are only defined for square matrices. This is a n by n. This is a n rows, one column. Okay. says lambda v. Lambda is a scalar, so either a real number or a complex number. We'll go into that later. And v again is the same vector that you put in. In this case, when if you find a non-zero vector that obeys this equation, where when you multiply it on the left by matrix multiplication, all it does is that it remaps that particular vector along the same direction, you could think of it, but it's just a multiple of the original vector. So it could either be longer or shorter, or maybe it's pointing in a different direction, but it's along the same direction. Then we call such vectors eigenvectors, right? So the vector v that satisfies this equation, the non-zero vector, right? Non-zero vector that satisfies this equation are called the eigenvectors or an eigenvector. And the value lambda or the scalar that you see in front of the vector is called an eigenvalue. Right? So that is the idea of eigenvalues and eigenvectors. We are interested in this special equation, AV equal lambda V. And when could we find non-zero vectors that satisfies it? The non-zero vector that satisfies it, or a non-zero vector, we'll see in a bit. If you get one of them, then you get a lot of them. It's called an eigenvector. And corresponding to each eigenvector, you have how much is it scaled by, and that is what we call an eigenvalue, right? And if you're wondering, like, why are they interested in this thing, AV equal lambda V? And well, it turns out that this sort of question comes up a lot in many different areas of mathematics and also science and engineering. You actually come across such questions in areas like when you're solving differential equations or when you're studying the stability of some sort of system that you're modeling. Um, is the system stable or unstable? If you have some, let's say, some population, and there are like two species, one is a predator and one is a prey. So one species is eating the other one. Um, uh, if you change the population of one of those by a little bit, so if you put two bits, then uh, do you get like a runaway sort of situation where one population just blooms, or maybe one of them just goes in extinct? So that's what I mean by the stability of a system, right? So this stuff, it comes up a lot in many different areas of mathematics, right? Um, yeah, and if you're interested more in this stuff, eigenvalues and eigenvectors, yeah, you do. We're just going to touch on a very little bit of it in this section. I'm just going to show you how to um, find it for special cases, for special cases where you have what I call non-degenerate eigenvalues. For the cases where you don't have that, we'll look at that in linear algebra 2. So in the second course in linear algebra, then we go a bit deeper into this idea of eigenvalues and eigenvectors. But just for this section, we're just going to look at, okay, how do you find such eigenvectors and eigenvalues for nice, easy matrices? And we'll also prove some a little bit of results involving them. Yeah, so what else do I need to say about this? Eigenvalues and eigenvectors. I think that's about it. We could jump back into the slides now. Oh, yeah, before we go back into the slides. So if you have any questions, you could feel free to um, ask it in the chat, or you could unmute your mic and just ask it. Yeah, so before we go back into the slides, just one more thing I want to mention. So I said that this equation here is the central equation in this section. AV equal lambda V, right? So essentially what we have to do is we have to solve this equation, right? For V and for lambda. So if you think about it, if we want to solve this equation, and of course, you know, A is a square matrix, right? And V is a column vector. Lambda is just some real or complex number, right? So we want to solve this equation, but what's the condition on V for non-zero vectors V? Remember, the zero vector will always satisfy this equation. We are interested in non-zero vectors. In fact, an eigenvector is defined as a non-zero vector satisfying this equation. So eigenvectors are not zero. Okay, the eigenvalue, so now you could ask, could you have a zero eigenvalue? And the answer is yes, you could have eigenvalues that are zero. Okay, so let's see if we just try to solve this equation for non-zero vectors V. What happens if I bring everything on one side of the equation? Right, so I move everything to one side, and now we need to remember that this is a matrix equation, so you can't put the number zero there. That is not the number zero. This is a matrix times a vector minus a vector. So this zero over here is a zero vector. Okay, it's just a column of zeros, column of n zeros, right? That's what that zero vector is. And they have the vector v in common, so maybe let me just pull v out, right? So now you're tempted to do a minus lambda times v. But does that work? Could you do a matrix minus a number? If I give you like 1001 minus 7, could you do that? No, you can't do that. So when we see it later when we talk about Cayley-Hamilton theorem, when you pull this v out, this vector v out to the right, you can't just leave this as a number. You need to sort of encode this number into a matrix in order for the arithmetic to work. So what you do is instead of writing the number alone, you do the number times the identity matrix, right? So this is the number times the identity matrix. Because now if I ask you to do this, minus 7 times the identity matrix is just a matrix with 7 on the diagonal, right? That's 7 times the identity matrix. Then you could do that, right? You could do that calculation. So just be careful there. Don't make the mistake of doing a matrix adding to a number, right? You have to now keep track of what are the objects you are dealing with. Okay, so all of these statements are if and only if statements. Okay, so we are interested in solving this equation a minus lambda I all multiplied by v equals 0, and we want for non-zero vectors v. Okay, now this matrix over here, I'm going to give it another name. Let's call this guy M. Right? Let's just call this guy M. So that's a new matrix. A minus lambda I, that's a new matrix. I'm calling him M. Okay, so I could rewrite this as MV equal 0. And hey, we know how to solve that, right? We did this in the systems of linear equations. I think that one was chapter 5. A matrix times a vector equals 0. Right? That's a homogeneous system. Okay. So that's the same as, right? That's the same as this one. All I did there was I just relabeled the matrix, this matrix. All I'm doing is I'm just calling this matrix M, right? I'm not doing anything fancy there. Now, what happens if this, so now forget all about these eigenvalues and eigenvector stuff. Look at this system. A matrix times a vector equal a zero vector. What happens if the matrix M is invertible? If this matrix M has an inverse, right? If M is invertible, in other words, a matrix invertible is a fancy way of saying M inverse exists. Then, if M inverse exists, then I could just multiply both sides of that equation by M. Sorry, by M inverse. Then I could just say that V is equal to M inverse the zero vector. Do you see that? If M has an inverse, then I just multiply both sides by M inverse. These two cancel, and I get V is equal to M inverse by the zero vector. And any matrix by the zero vector gives the zero vector. Okay, so what do we get there? What are we showing here? We are saying something very and this here lies the this here is the whole idea in how to calculate these eigenvalues and eigenvectors. If the matrix M is invertible, that is, if M inverse exists, the only solution to this problem is V equals 0. If M inverse is invertible, sorry, if M is invertible, the only solution is the vector is 0. Do we want a 0 solution? We want a non-zero solution. So we only get these solutions that we are looking for if M is not invertible, right? Because now you all are so used to wanting the matrix to be invertible, but now this is sort of like a change for that. Now we want the condition is the matrix M cannot be invertible, right? So this is the same thing as saying the system. So let's go back to the what M is. So M I defined to be A minus lambda I, right? Times V equal 0 has non-zero solution, right? If and only if the matrix M, right, which I label A minus lambda I, this matrix is not invertible. Okay, so when we are solving the system, AV equal lambda V for non-zero vectors V, we own the solution to this system only exists if and only if this matrix A minus lambda I is not invertible. Okay. Otherwise, the only solution, if A minus lambda I is invertible, the only solution is the zero solution. And we don't want the zero solution. We are looking for other vectors. Okay. Now, we just came out of looking at determinants. And there's a result that you also may have met in high school, which is if a matrix is not invertible or does not have an inverse, what does that mean about its determinant, right? Since I'm doing if and only if, let me do the double implication, right? So if I tell you a matrix is not invertible, what could you tell me about the determinant? Then the determinant of this matrix, A minus lambda I, that's the matrix M, should be 0. Right? A matrix is not invertible if and only if it has 0 determinant. So what we just did there was the first proof in this section, actually, which is how do we solve this equation, AV equal lambda V, for non-zero vectors V? So that is if and only if all of these conditions you go two directions. That is equivalent to solving this, the determinant of this matrix, this new matrix. So we don't solve for the determinant of the matrix A, right? We don't solve for the determinant of the matrix A equals 0. We solve for the determinant of the matrix A minus lambda I equals 0. That is how we find these eigenvalues. Okay, so if I tell you find the eigenvalues for matrix A, this is the equation you need to solve. The determinant of A minus lambda I equals 0. Right? So that's the central equation in this section, and it's so important they give it a name. This left-hand side here. So we didn't show this, we didn't prove this. It's actually a bit kind of in depth to show this. But the determinant of a matrix like this turns out to be a polynomial. Right? So the determinant of a matrix A minus lambda I, lambda is the unknown, by the way. Lambda is the unknown. Turns out to be a polynomial of degree n. So if the matrix is, let's say, 5 by 5, the determinant of A minus lambda I, when you work out what that is, you'll get a 5th degree polynomial in lambda. Okay. So this equation is so important. They give it a name. They call this the characteristic polynomial. Characteristic polynomial. Okay. And when you set the characteristic polynomial equal to 0, which is what we are doing, right? We set it equal to 0. Okay, maybe I do understand. This thing here, the entire thing, the characteristic polynomial equals 0. The entire equation is known as the characteristic equation. Okay, so that's the characteristic polynomial, and now you see where it comes from, right? This is the proof of the characteristic polynomial. This is why, well, we'll see in a bit when we go to study this. We'll see why. Why are we solving for the determinant of A minus lambda I equals 0 to get the eigenvalues? This is the proof. Right? This shows how to derive this thing called the characteristic polynomial. And when you set the characteristic polynomial equal to 0, you get the characteristic equation. Right? So nothing complicated we did so far. Right? So very basic stuff we're doing so far. Yeah, so any questions so far? No. Right, so solving the characteristic equation will give you the lambdas, right? It will give you the lambdas. And how to get the v's now. So that's usually the problem. Okay, so we'll go through the slides now. So the first few slides is what I just explained there. So I'll just you'll see this. Yeah. Right. So the first few slides is what I just what I explained there. Right. So let's just quickly recap it. So if I give you a matrix A, so this means the entries in your matrix come from the field F. So when we talk about eigenvalues and eigenvectors for a matrix, that matrix needs to be square. Okay, it has to be a square matrix. Why? Because you just saw in order to get the eigenvalues, you need to solve a determinant. Determinants only exist for square matrices, so it needs to be square. Okay, where F is any field. So for usually the field that is used in this case is the complex numbers. It turns out if you don't use the complex numbers and you use the real numbers, then you run into a lot of problems. But to do the calculation here, we're only pretty much going to look at the calculations for when we get like real values. Because when you get complex eigenvalues, then your eigenvectors now are complex eigenvectors, and that's like a whole thing. So that we will do in linear algebra too. Okay, where lambda, right? So an element lambda is called an eigenvalue or a characteristic root of A if there exists a non-zero vector. So they call it X, I called it V, but you could call it whatever you want, such that AX equal lambda X. Right? So this is also sometimes called the eigenvalue problem. This corresponding vector X is called an eigenvector or a characteristic vector. So for an eigenvalue, lambda, right? So let's sort of break this down. What is this? The null, remember, null means the null space. The null space of A minus lambda I. So this A minus lambda I, remember where we got that from? A minus lambda I. We saw that somewhere, right? That was this matrix that I call M, right? And what they're saying there is that V here represents an eigenvector. Where do these eigenvectors live? So if you think back to when we studied the null space of a matrix, the null space of a matrix is the solution set of all vectors V such that M times V equals 0. So if this is true, then we say V belongs to the null space of the matrix M, right? And what was M? M was this matrix that I call A minus lambda I. Okay. So the eigenvectors, where do they live? They live not in the null space of A, they live in the null space of A minus lambda I. That's so the eigenvectors we'll see form a subspace. Okay, because the null space of a matrix is a subspace, right? And it's called the eigenspace. Right? So for a particular eigenvalue, the null space of this matrix is what I was calling the matrix M, okay, which is a set of vectors X such that A times X equal lambda, A times X equal lambda X is called the, so instead of saying the null space of this, they call it sometimes the eigenspace. This is where all the eigenvectors live, right? Eigenspace of A corresponding to lambda. This is the vector space of all eigenvectors that correspond to an eigenvalue, lambda. Right? So what do they mean by all eigenvectors corresponding to an eigenvalue, lambda? Right? Because I thought for every eigenvalue, you get one eigenvector. No. For every eigenvalue, you get an entire space of eigenvectors. Right? And you can actually prove that. So for example, right? I think this is maybe later on, but let's just do it now while it comes, since it came up. So I don't know what result it is. I'll just call it result. If V is an eigenvector of the matrix A corresponding, so when we talk about eigenvectors, you usually have to say eigenvectors corresponding to what eigenvalue. Because when you change the eigenvalues, you get different eigenvectors. They come in pairs. You get the eigenvalue with its eigenvectors. They're called an eigenpair, right? We'll get into that later. So if V is an eigenvector of A corresponding to an eigenvalue, lambda, I claim that any multiple of this vector V, any non-zero multiple, I should say, is also an eigenvector. Then, what letter do I want? I don't want to scare you all with another Greek letter. Okay, let's do A, right? And A times V, right? Where A is a non-zero scalar, is also an eigenvector. So I'm saying if you have a vector V, that's an eigenvector, then any multiple of V is also an eigenvector, right? And the proof of this is very easy, right? It's an one-line proof, right? So suppose V is an eigenvector for lambda, then by definition, what does that mean? It means A times V equal lambda V. That is what it means to be an eigenvector V for an eigenvalue lambda, right? We call this guy 1, and now we just say consider. Actually, we could even do it over here. Let's just multiply both sides by A. Okay, so let A be any non-zero scalar, right? Any non-zero number. Multiply both sides by let's see, green. A multiplied by A times V equal A multiplied by lambda V, right? And what do you all think we're going to do? We're just going to push A into V, right? Because this is when you're doing matrix multiplication, you know that you could pull numbers inside and outside. Well, at least now we know, right? So you can move. What I'm saying is that you can move this A inside, right? Because A is a scalar, so you can move A inside. A, remember, A is a matrix. Matrices are linear transformations. And linear transformations, you can move scalars back and forth. Yeah, so this becomes A, right, into AV, right, equal lambda into AV. So if you want to, you could relabel A times V as, I don't know, W or something, right? So you could relabel it as W, doesn't matter. AW equal lambda W. What is that? That's the equation for an eigenvector, right? Where W is non-zero, right? W is non-zero because V was an eigenvector. If you are an eigenvector, you cannot be zero. So V is not zero. Is A zero? A is not zero. So A is not zero, V is not zero, therefore their combination is not zero. Okay, so what I'm saying there is W is not zero, right? Because A is not zero and V wasn't zero. W is not zero. That means W, which is really AV, is an eigenvector. right? That's the equation for the eigenvector. It's an eigenvector um, for lambda, right? Ax equal lambda x. In this case, we have W. Okay, so yeah. So again, what did we just show there? We showed that if you have an eigenvector, then any multiple of that eigenvector is also an eigenvector, right? And you could also think of if you have two eigenvectors, is the sum of them um, an eigenvector? Also, if V1 and V2 are eigenvectors for eigenvalue lambda, then what happens if I do, let's look at what is A multiplied by their sum. And let's look at what we get. So add them together. Add two eigenvectors together and then apply A to it. Okay, so we know to do this, then A is a matrix, so it just, distributes over each one. So we get A V1 plus A V2, okay? And V1 and V2 are eigenvectors, right? So eigenvectors mean A V1 equals lambda V1, okay? Since A V1 is an eigenvector. So eigenvector means Ax equal lambda x. And A V2 equal lambda V2. So I'm just using that property here, lambda V2. And lambda is a scalar, so I could pull lambda out to the front. So what do we just show there? If you call this guy W, and you look W here again, then what am I showing here? I show that AW equal lambda W. In other words, W, which is really V1 plus V2, is an eigenvector, right? Because it satisfies the eigenvector equation. So what have we just showed there? We showed in the first part, if V is an eigenvector, then any multiple AV is also an eigenvector. If V1 and V2 are eigenvectors, then their sum is an eigenvector. So what does that mean? The space of eigenvectors is a subspace, or you could say a vector space, right? So that's what we showed there. Therefore, the space of all eigenvectors, now I have to put a little condition here with the zero vector, right? Because remember, technically the zero vector is not an eigenvector, but you need the zero vector to be a vector space, right? Every vector space, every subspace needs a zero vector. But I said the zero vector is not an eigenvector. So that's okay. I'm just going to throw the zero vector in, right? So the space of all eigenvectors with the zero vector is a subspace, right? This subspace is given by, so what is the subspace? Is there a nice, easy way to write this subspace? Yes. The subspace is given by this space. It's the null space of A minus lambda I. And the null space of a matrix is equal to the set of all vectors V belonging to n rows, one column, such that the null space means A, it means the matrix, right, by the vector equals 0. That's what the null space means. But this condition here, you all know what this condition really means. If you unpack it, if you expand everything out and move stuff around, you all know that this condition is the same as saying AV equal lambda V, which is the eigenvector equation. So we showed a lot here so far, right? We actually did. I know we're not technically going through the slides, but this way, all of this information is in the slides, right? But I'm just deriving it back here systematically. So what have we done? Let's just do a quick recap of what have we done. So we started with the motivation of the example in R squared, where we were looking at vectors as arrows, right? So to each point, there's a vector. To each point, there's a vector. To each point, there's a vector. And I defined a linear transformation from the space into itself by simply taking that vector and multiplying it on the left by a matrix. In this case, since we are in R squared, the matrix will be 2 by 2. But again, all of this holds for any n-dimensional space, for any Rn. This will work. I'm just doing 2-dimensional here. And what this multiplication does is it converts this vector xy into a new vector, x prime, y prime. So maybe it moves this vector over here, right? Or maybe it moves this vector up here. But we were searching for, are there special vectors such that when you left multiply by A, the new vector lies on the same line as as V, but it's just scaled down or it's scaled up. Or maybe it's in the opposite direction. In other words, we were looking for cases where when we did a matrix times a particular vector, we get some scalar multiple of the vector that we put in. And I said that it will always work if we take the zero vector. The zero vector is one such vector. But we don't care about that. I don't want the zero vector. I want to know, are there any non-zero vectors that obey this equation? And this is, again, what we will call the eigenvalue problem. It's usually denoted as the eigenvalue problem. And any vector that satisfies the eigenvalue problem, any non-zero vector, right, is called an eigenvector. And the corresponding multiple that it comes out as is called an eigenvalue. So we say that V is an eigenvector corresponding to the eigenvalue lambda. And now the task became, okay, that is my definition for the eigenvector. That is my definition for the eigenvalue. How do I find these things now? If I give you a matrix A, how exactly are you going to find these things? And that's the calculation we did here. We started with the equation AV equal lambda V, and we want to solve this equation for non-zero vectors V. So we took this guy on this side and we pulled V out to the front and we relabeled this matrix M. And we saw that trying to solve this equation, AV equal lambda V for non-zero V, is equivalent to solving this equation, MV equals 0, where M is this equation, is this matrix here. But if this matrix M is invertible, that means if it has an inverse, then the only solution of V is the zero solution. But we want a non-zero solution. So therefore, we say that the system that we are interested in has a non-zero solution if and only if this is the matrix M is not invertible. And we know from the previous chapter on determinants, or maybe you know this from high school, that if a matrix is not invertible, its determinant is equal to 0. And this determinant, so now we know I is the identity matrix, 0. Well, which 0 is this actually? I said the determinant of this matrix equals 0. Is this a 0 matrix? 0 vector, the number 0? This is the number 0, right? This is a scalar equation. The determinant of a matrix is a number, right? So this is the number 0, right? That's the number 0. So the only unknown here is lambda. So I said when you unpack this guy, you will get a polynomial in terms of lambda. Lambda is the unknown. That polynomial we call the characteristic polynomial, and the entire equation we call the characteristic equation. So to solve for the eigenvalues, lambda, we solve the characteristic equation. Okay, I'll show you in a bit how to get the eigenvectors, but that's how to get the eigenvalues, right? So now we'll start looking at the eigenvectors, okay? And I said that if V was an eigenvector for the eigenvalue lambda, then any scalar multiple, any multiple of it, of course, any non-zero multiple, I said is also an eigenvector. So you could take eigenvectors and you can multiply them by non-zero numbers and you get an eigenvector again. Okay, so to each eigenvalue, lambda, there are infinite eigenvectors. All you have to do is for each eigenvalue, you take an eigenvector and any multiple of it is also an eigenvector. So there are infinite eigenvectors for that particular eigenvalue. And why is any multiple of an eigenvector again an eigenvector? Here's the proof, right? So we prove that. And not only you can scalar multiply eigenvectors to get eigenvectors. If you take two eigenvectors corresponding to the same eigenvalue, right? They need to correspond to the same eigenvalue, and you add them. The result is also an eigenvector. So if you have an eigenvector and you add it, you get a new eigenvector. If you have an eigenvector and you multiply it by any scalar, you get an eigenvector, well, any non-zero scalar again. In other words, the space of all eigenvectors with the zero vector added in was a subspace, right? That's the subspace test. Okay, the subspace test is when you add two vectors, does the new vector belong to the space? Yes, the new vector is an eigenvector. If you take any scalar multiple of that vector, is the new vector belong to the space? Yes, a multiple of eigenvector is an eigenvector. And the third condition is the zero vector in the space? Well, I am adding it in. Right? That's why we need to add it in. And this subspace, I said there's a nice, easy way to write it. It's given by this. It's the null space of this matrix, which I was calling M. It's nothing but the null space of that matrix. Right? So that's a recap of where we are so far. We know how to find the eigenvalues. Right? We solve the characteristic equation. That's how to find the eigenvalues. And the eigenvectors, they all live in this space. Right? The eigenvectors live in this space. So if you know an eigenvalue lambda, you can plug it into here and you know everything here because you know I is the identity. And if you know, let's say you work out, I don't know, lambda equals 4 as the eigenvalue, then you know everything here. And you can then get the null space of that matrix. So, what lives in the null space? The eigenvectors. So this is how to find the eigenvectors, right? This is how to find the eigenvectors. This is how to find the eigenvectors corresponding to eigenvalue lambda. You need to solve for the null space of this matrix. That is, you take the lambda, you multiply it by I, and then you take the matrix A and you subtract lambda I. And this new matrix, if you want to, you could call it M. You need to then work out what are the solution of M, okay, let's go X equal 0. You need to find these X's, or at least one. If I ask you, hey, I don't want all of them. I don't want the entire space, just give me one. Then you just need to find one possible value of X in the null space of M. That's what this equation means. Okay, so we actually just covered there how to get where the characteristic, so we covered there actually we covered a lot. I think we covered most of the information in that in the slides. We covered the motivation behind eigenvalues and eigenvectors, what the eigen problem is, what an eigenvalue and an eigenvector is, what is the characteristic polynomial and characteristic equation, how to get the eigenvalues, and the motivation behind, or the proof, I should say, behind the eigenvectors being equal to the eigenvectors living in the subspace, which I am saying is a way to find the eigenvector. So now we know how to find the eigenvalues and the eigenvectors. Okay. Yeah. So this theorem here is what we already proved. This theorem is saying lambda is an eigenvalue of A if and only if the determinant of this matrix equals 0. So we proved that. This is the matrix that I call M, right? We already proved that, right? And we proved it in a lot more detail because you see over here, it's just like 2 lines and then I put like a Y here, right? So I have it, we did it in much more detail before, right? This one, they are talking about what the characteristic polynomial is. Okay, we did that. The characteristic equation, okay, we did that. That the eigenvectors live in this space, okay, we did that. And that the eigenspace of lambda is the solution set of this equation, okay, we did that. Right, so now we did all of that. So now let's do an example, right? Let's apply everything that we just did. Here's a matrix A. We'll start with simple 2x2 matrices, but you could do this for any square matrix. Let's just start simple 2x2 matrix. And let's see how to get the eigenvalues and a corresponding eigenvector for this particular matrix A. Okay. Now there's something I should stress here, and that is, you see in these problems where when we ask for eigenvalues and eigenvectors of a matrix A, you have to pay attention to where the entries are. Where do the entries of your matrix live? So you see this matrix A belong to R2x2. In other words, the entries are real numbers. So you're saying, okay, well, I knew that. I knew the entries were real numbers, right? So what is the big deal about whether I put R over here, or maybe C 2 by 2, complex numbers? What is the big deal here? Sorry, I realized that I didn't write it here. But it's in the notes, it's in the definition. And that is the eigenvalues. Where is my eigenvalues? Yeah. The eigenvalues need to come from the same field as the entries in your matrix. So what does that mean? That means if the entries in your matrix are only real numbers, then the eigenvalues could only come from the real numbers. If the entries in your matrix, you allow it to be complex numbers, then the eigenvalues can be complex as well. Okay? So when you see R 2 by 2 over here, if it happened in this calculation, let's just say if we happen to get an eigenvalue, say we got an eigenvalue lambda equal to I plus 1. Can we take that to be an eigenvalue? When we solve the characteristic equation, say we get lambda equal I plus 1. It's because the entries in the matrix was explicitly defined to be entries only in the real numbers, right? So it's usually written like this. A belongs to F n by n, then for lambda needs to belong to the same field. In such a case, even though this pops out as a solution, you cannot take it as one. You could only take eigenvalues in the real numbers. Okay? And now you might be thinking, well, that's not a big problem because this matrix, yes, it belongs to R 2 by 2, but it also belongs to the complex numbers because every real number is a complex number, right? For example, the real number 7. 7 is a complex number. 7 is equal to 7 plus 0i. So every real 2 by 2 matrix is also a complex 2 by 2 matrix. So we could just replace R here by C 2 by 2, and then we don't have a problem. Yes, you are correct. We could do that. Okay, but it's just something to keep in your mind, that you need to look at where the entries of your matrix are defined, and that field is where the eigenvalues have to come from. Right? So right away, this is telling me if I get any complex eigenvalues, I cannot take them. I need to throw it away. Okay, so I hope that was clear. Okay, so to get the eigenvalues, so there's a couple of examples. Yeah, so we just do the first example, right? Because we have enough time to finish this. So we just do the first example and I'll let you all go. So we have the matrix A, 1, 2, 2, minus 2. To get the eigenvalues, that's the first task. We need to get the characteristic polynomial. Remember, the characteristic polynomial is given by the determinant of A minus lambda I. Okay, so that is the determinant. Okay, so let's first work out what is this. A minus lambda I. That is 1, 2, 2 minus 2. That's A minus lambda I. Lambda I is lambda by the, in this case, it's the 2 by 2 identity matrix. Okay, so that's just lambda 0, 0, lambda. So lambda I is just the identity matrix, but instead of ones on the diagonal, you have lambdas on the diagonal. And this gives 1 minus lambda, 2, 2 minus 2 minus lambda. So that's where they got this guy from. 1 minus lambda, 2, 2, minus 2 minus lambda. Okay, this here is the matrix A minus lambda I. There's a quick way to do this, by the way. When you have to work out A minus lambda I, the quick way, it's the matrix A It's the matrix A. This is the matrix A. 1, 1, 2, 2, 2, 2, minus 2, minus 2. This is the matrix A. And how do you do A minus lambda I? You subtract from the diagonal entries lambda. That's all. To get the matrix A minus lambda I, take the matrix A, subtract from each diagonal entry, you subtract lambda. That's the quick way to get it. Right? Okay, so it's a determinant. You all know how to do determinants of 2 by 2 matrices. It's this one by this one, minus this one by this one, which is minus 4. So expand, and you get a quadratic polynomial. Remember I said this determinant, the characteristic polynomial is a polynomial of degree 2. Why 2? Because it's a 2 by 2 matrix. It's a polynomial in terms of lambda, which is the eigenvalues. And usually we write it as P lambda, right? P lambda. Maybe I should put that in here. Characteristic polynomial. Yeah. So this is usually denoted as P lambda or P of lambda. Right? We usually call the characteristic polynomial P of lambda. P for polynomial, lambda because lambda is the unknown. Okay. And this could factorize. Of course, I'm not going to tell you what to do if it doesn't factorize. You all know to use quadratic formula or whatever. So to get the eigenvalues, you need to solve this polynomial equals 0. So find the roots of it, right? You all know to find roots of a polynomial. So get the roots of this polynomial, that is lambda equal 2 or lambda equal minus 3. These are the eigenvalues. So it turns out for this matrix A, we have 2 different eigenvalues, 2 and minus 3, right? So now how do we get the eigenvectors? The eigenvectors is the same calculation for both of them, just slightly different numbers. So take one of them. Let's get the eigenvectors. Take one of them. To obtain the eigenvector that corresponds to each eigenvalue lambda, we need to find a solution to the homogeneous system, right? We need to solve this. This equation you see here was the same thing, mx equals 0 that I wrote. Why did I write mx equals 0? Now I'll put that somewhere. Maybe I didn't write it. Oh, yeah, over here. See, I remember I wrote it somewhere. Well, I put mv, right? So that's what we need to solve. In other words, V belongs to the null space of that matrix. Okay, so you need to find values of x that satisfy this equation. So again, we know what lambda is. For lambda equal 2, take 2 and plug him in over here. So work out what is the matrix A minus 2 lambda. And I told you the easy way to do it, right? It's the matrix A, but you subtract 2 from the diagonal. And this is your matrix. So this is the matrix M. This is the matrix M that you're working with. You need to get the null space of M. That's where the eigenvalues are. So we now solve for the null space of this matrix M. Right? So what you need to do is you need to solve for need to solve this system. So let x be the vector x1, x2. Or you could do a, b, anything you want. x1, x2, and you need to get the null space. The null space means the right-hand side is 0. So from here, you could write down a system of equation, minus x1 plus 2x2 equals 0, and 2x1 minus 4x2 equals 0. Solve. Solve that, right? Or if you want to, you could do row reduction, right? Whichever one, it's up to you. Whichever one you want to do. So they're doing row reduction. So they took the matrix here, and they did row 2 goes to row 2 minus 2, plus 2 row 1, and you get 0 row. Now, when you try to solve this, I know you're seeing 2 equations, 2 unknowns. These aren't really 2 equations, eh? You will always get, you will never, when you try to solve this, you will never get one solution. The reason you will never get one solution is, what is the property of this matrix M? Does M have an inverse? Remember, by construction, M does not have an inverse. This matrix here, we got values of lambda such that this matrix M does not have an inverse. So when you go to solve this system, you don't expect to get a unique solution, because this matrix is not invertible, right? It's not invertible because we constructed it to not be invertible. If it was invertible, the only solution will be x1 equals 0 and x2 equals 0. So it's not invertible. That's why you get a 0 row, right? You'll get infinite number of solutions. Of course, you will get infinite number of solutions because each solution represents an eigenvalue, an eigenvector. How many eigenvectors are there? They are infinite. They form a subspace, right? So of course you will get infinite number of solutions. So when you're doing these questions and you get the eigenvalues and you say, okay, great, now I'm going to get the eigenvectors, and then you're like, wait, did I do something wrong because I'm getting a 0 row and I'm getting infinite number of solutions? No, you did the correct thing. You will get infinite number of solutions because each solution is an eigenvector, right? So when you try to solve this, you will get the whole free variable kind of thing. Okay, let's go through it. They have it here. So you say we're going to let x equal x1, x2 transpose. Then this system, right? So all they're doing is they are just putting x1, x2 equal 0, 0. And from here, when you work it out, you get minus x1 plus 2x2 equals 0, or x1 equal 2x2. So x2, so now it is your choice. Which one you choose as your free variable, that is your choice. Let's say x2 is the free variable. Okay, it means I'm going to write my solution in terms of x2, right? So therefore, the solution, where do the eigenvectors live? They live in the null space of this matrix. And the null space of this matrix is what we just solved for. It is all vectors of the form x1, x2, right? Such that, well, technically it's transpose, such that A minus 2I x1, x2 transpose equal 0, 0 transpose, right? For x1, I know is 2x2. So I could take him and plug him in over here. Okay, so that becomes 2x2 comma x2 transpose, where what is the restriction on x2? No restriction. any real number. Or they have x2 in common, so pull x2 out, x2 into 2, 1 transpose, where x2 is any real number. Or that this you should recognize as all scalar multiples of 2, 1, which is nothing but the span of 2, 1. Right? That is the eigenspace. Okay, so you already know how to do all the calculations in this section. You already know how to do, because all the calculations is just how to find the null space. It's just how to solve the system mx equals 0. And again, and with solving this, you will have to choose a free variable and write your solution in terms of that free variable. Okay, so if they ask for a eigenvector, if the question say, okay, give an eigenvector, what we gave here was the full big eigenspace. If the question say, I just want just one eigenvector, then no need to do all this. If the question says, hey, just give me one eigenvector, we could get that eigenvector from here. Just pick any value of x2. So say x2 is 1, then x1 is 2. Right? If x2 equal 1, this means x1 is 2x2, which is 2 by 1, which is 2. Therefore, the vector x1, x2, which is, in this case, it's 2, 1, is an eigenvector. And you're done. Okay, so if the question say, just give me one eigenvector corresponding to that eigenvalue, this is all you have to do. No need to get the full null space sort of thing. But if the question says, give the eigenspace, then you need to write down this full null space stuff. Okay, of course, once you have the full null space, all you have to do is just take any vector in here. So pick any x2 and you get it. Or if you want to, you could pick 2, 1. Right, because it's a span of 2, 1. Right, and that's the eigenspace corresponding for lambda equal 2. Now we had another eigenvalue, lambda equal -3. So how do you think we get the corresponding eigenvector for -3? Same calculation, same thing. You will got a minus, so it will be -3, which becomes +3i. So form this equation. This is your m. Then you need to solve mx equals 0. Right? If you want to, you could solve the equations, or if you want to, you could write the matrix and reduce it. That's up to you how you solve it. Right? I don't care how you solve it. Right? So what I'm saying is, if you want to, you could write this x1, x2 equal 0, 0. This implies 4x1 plus 2x2 equals 0, and 2x1 plus x2 equals 0. So you need to notice that this is really one equation, because the first equation is just 2 times the second equation, right? So you just have one equation, which is 2x1 plus x2 equal 0. So one equation, 2 unknowns, pick your favorite variable. Let's say x2 is equal to -2x1, right? Therefore, the solution look like x1 comma x2 transpose, but x2 is -2x1, so we get x1 minus 2x1 transpose, x1 in common, so -2 transpose, right? So it's the span of 1 minus 2 transpose. An eigenvector, just pick any value for x1, any not that doesn't give 0, by the way, right? Because eigenvectors cannot be 0. So here's an eigenvector. Okay, same thing, same sort of calculation, right? So once you understand how to do the null space from the previous chapter, same story over here. Because what new calculation did I teach you all to do? Because we know how to get the null space of a matrix, that was in chapter 5, and you all know how to solve a quadratic polynomial, right? That's from high school. So what new stuff did you learn? Nothing. None of this is new. Well, none of the calculations is new. It's just the theory behind it, right? That I had to explain. Okay, so we'll stop there for today, right? Next time we'll look at this is the ideal case, two different eigenvalues. Next time we'll look at what goes wrong. Okay, are there any questions?